Good afternoon, everyone. I can't believe it's the end of June already, but here we are on our webinar number 57. And today we have a guest presenter, well known to you all, Tony Smith, on the subject of measure, maintain, enhance safety and save money. As usual, we have the panel today of Carl Johnson, senior aviation lighting specialist with a wealth of experience in design, construction and maintenance. Stuart Ford, independent specialist consultant with a lifetime AGL knowledge, Christ Hines, and then AAA trainer and now an independent consultant working on projects such as the introduction of LED lighting. And of course, our star of the show, Tony, who will be joining us today to actually give the guest presentation, which was recorded to recount his experiences of the understanding of the purpose behind every light and how that will help the airports improve lighting, improve safety, optimize maintenance, demonstrate compliance, and potentially reducing costs. So I hope you enjoy this. Thank you, Tony, very much for doing this for us.
This is very personal presentations, I'm saying, from a long background of working in visual aids work. And so I thought a visual aid is something we give to the pilot to enhance what he gets from the natural world. And you should be able to use them to enhance what he normally does. If you give him a visual aid and he has to train on very specifically to use it occasionally in low visibility, when it comes to it, in the stresses of those environments, the training will go out of the window and revert to a bog standard sort of human being. It's got to be compliant with what you normally do in life. Well, the first requirement for visual aids, if you like, we go right back to the beginning of aviation. Before World War I, I suppose the main emphasis was on, well, can we make aeroplanes reliable enough to go from A to B, more than the short journey of 2 or 3 miles. And so in UK there were air races, and there was one, I think, in about 2012, Manchester to London. And my parents, who lived in the countryside near the railway line that went from Manchester to London, went up the church, went up onto the tower at the top, so they could see these airplanes flying down railway. That was their navigational aid. They followed the railway with a map on their knee. That was the first visual aid. Was what they saw naturally from the real world. When they got to the World War I, and aeroplanes, some people in particular see the value of them for spotting and aerial warfare as well. Very constrained, but basically it was all right as far as taking off and landing was concerned, in good visibility by day. But of course, in the warfare environment, you really wanted to operate in as much different types of weather conditions, poor weather conditions, and certainly at night. And they couldn't do it because they got no means of doing it. And so in the very early days, there was a great need for visual aids, but nothing was really being done to provide any. So if we go on then to the 1920s, after the First World War, two areas that developed rudimentary visual aids was typified by what happened when Lindbergh flew the Atlantic and landed in Paris. He arrived at night, and so to enable him to land, the people that came to meet him went with their cars and lit a strip of the airfield, the grass strip. They floodlit it. That's an obvious way of, and the pilot said, I want it in the night to see what I see in the daytime. So floodlight, that was one way of doing it. That was one example of an attempt to do it. Another interesting thing that happened in those periods was the barnstorms. The old First World War pilots who were making money with an aeroplane, going from place to place, putting on an air show, doing a sort of stunt flying, and then taking people airborne for 30 minutes. And particularly very, very popular in the United States, but also in Europe. And what they found out, one thing in context of all-weather operations, was often, you know, if there was fog and so on, how were they going to get to the next town, 50 miles away, for the next day's performance. They found, again, they could follow the telegraph poles from A to B in low visibility, flying very low, of course, and this is Napoli flying over the terrain, provided they could see a certain number of telegraph poles. That was their basic, that was the safe limit, count number, and it approximated to about 500 feet. They could manoeuvre, they're slow aeroplanes. And that bit of information actually was fed into the early specifications for what lighting do you need to see in low visibility to make a decision to continue to land. If, when I begin to see the ground, if I can see enough lights to say I can see 500 feet ahead of me, then I can probably make a decision that I'm going to be able to land. So that actual bit of information, which was gathered sort of on the hoof, as it were, by pilots who weren't test pilots, was actually a very useful bit of information in trying to get all-weather operations going later on. And then, towards the 1930s, people began to say, well, we must do something more. What about using other non-visual guidance methods we can use in addition to visual aids, and the very early days of things that eventually became ILS, and of course by 1940 radar had come along. There were things that were going to enhance the approach, but you'd still got to do the final bit manually anyway. And so in that period, the idea that there should be a long-term goal of all-weather operations, 0-0. It was a long way off, they didn't know how to do it, but that was the goal, to do that. And so the attempts in the late 30s and early 40s, these couple of diagrams are from a paper I have written by Calvert, whose name you may know from the approach lighting. He was a big person in putting the science into some of this in the 40s and 50s, and was really the chief architect behind the first lot of visual aids that went into Heathrow. The taxiway centreline lights, follow the greens. That was quite novel. For many years, nobody else was interested. It was just Heathrow's wonderful way of getting around in reduced visibility at night. Certainly, in the period of the late 30s and early 40s in the wartime, there were attempts to make it possible to operate in what I call marginal visibilities, a sort of weather we've got today. When the American Air Force came to Great Britain, they'd trained in the Arizona desert or somewhere, and actually found it quite difficult to actually find the airfield. They weren't used to that sort of environment, and that was where the first high-intensity lighting actually was. It was a big sodium floodlight stuck on the end of the runway. They put on, 8,000 candelas. It was a sort of beacon they could find, but in an attempt to provide some sort of standard, the RAF had a development which is shown here. This is the sort of middle, latter part of the war. You can see the runway there, the dots, lights down the side of the runway, a little bit of approach lighting, a slight sort of funnel thing, and then this big circle of lights. And I can remember living near an airbase, and I remember no idea what these poles in the middle of the fields were for. But they were for pilots to join the circuit. They go round and round and round that till they got a signal, a vari light, that they could land, and then they'd line up on the runway and land. But all low intensity. There was a glide slope indicator, three colour device, but it was only 1,000 candelas. It was just very much twilight marginal stuff. It really wasn't anything like low visibility. But it's interesting. This part of in the United States that there was this attempt by a gentleman who suggested, and you can see some concepts that are right, of parallel rows of lights to line up with and designate where the runway is, a man called Burroughs. And those were more high intensity lights, but the beam spreads were very narrow, if you look at it. That's all in my report, and more easy to read there. But you can see they're groping without really doing much scientific work to try and get something that would enhance the visual aids in these marginal conditions. So, I've said the appliance of science. I think this is really from 1945 to 1970. There was an attempt in various places. The FAA put quite a lot of effort in. The UK certainly had a very big input. We had a blind landing experimental unit set up in 1945. I was part of that from the early 1970s to develop approaches such that we could have 0-0 landings and takeoffs. And the UK was one of the leading nations developing those numbers that now you see in terms of decision heights and RVRs and visibilities and so on. But even then, understanding what fog was actually like and how it actually impacts, that took a lot of learning. And I had a colleague who worked for me in the 80s, 90s. He was real good. He spent his time really understanding the structure of fog and how it interfered with actual lighting. And he produced in the end some models of fog that were realistic of what pilots actually see. We actually understand why it was that we saw what we saw. You see what I mean? And it was, I say, the scientific approach. The engineering approach is, I've got a problem here, and I said this particularly in the States, ask 50 companies for their best ideas, and you look at all of them, and you choose the best one, you call that the standard. But without any relationship really to what's the operation, you just take the best one. It might be inadequate, but but the scientific approach is just, well, first of all, let's understand what the problem is. Why are we finding it difficult? And what are the elements? And that's what a lot of effort was put into. And Calvert built himself a very early simulator where he could put pilots into it and see different patterns of light, and by questioning and sometimes showing them what it was they were actually using, how they were using the patterns, what patterns work. Curved patterns, like I showed earlier, it's actually quite difficult to follow a curve of lights. The best thing, and not funnels of lights either, arrowing thing. You want he established that you want parallel lights on the runway edge, that's fairly obvious, but the approach lighting as well. And basically the approach, you have lights that are parallel to your direction of land or across it. Curved lights and not a good. You may think sitting in an office, oh, I'll put a circle of lights around it. It's not good, not easy. Sometimes you're forced to do that, and in ICAO or something, but it's not easy. You want a nice long straight approach with some visual aids that are readily interpretable, and that's what I say was so important. And one thing, again, was found out, and this was in, let's say, marginal weather and down into category 1, a glide slope indicator. If you're going to have a stable approach, which you need for a good landing, a repeatable landing, not landing very long, but landing more or less in the right place, it all begins with a stable approach, and a good glide slope indicator is needed. And that's where the Varsi was first invented by Calvert. It was a first attempt. There are limitations on it, which I'll go into later, if you like, after the meeting. But it was established that any visual aids for the approach and landing needed to have a glide slope, because you can't judge height. You can judge left-right. We're all used to walking down corridors and driving down roads. Driving left-right, but in the third dimension, where there isn't a line, as it were, in space, you do need some visual aid to enable you to do that. So, some more of the fundamentals. Important, as I say, that pilots do what they can. We learned this. Pilots do what they normally do, maneuvering the airplane in low visibility. I have to say, the visual aids developed over the period around the 1970s as the pressure was to get all-weather landing, and that required an ILS, an autopilot in the airplane, and their performance wasn't that brilliant at the time. So all the while, how do we gradually reduce the decision height and the RVR? There was a program, a controlled reducing perhaps the decision height, then reducing the RVR, and it was a gradual process to get from what would be the standard of 200-foot decision height and half a mile. That was sort of what you got in the 1940s, often by a talk-down procedure or early ILSs, but largely a talk-down procedure, and a cloud base of 200 feet. That was, and there were a lot of accidents actually at that point, and the objective was taken then that if we were going to do automatic coupled approaches and landing as low visibility, the safety record was it had to be, in terms of the number of fatal accidents, had to be 10 times less than the world average for accidents on the approach. In other words, the number was about 1 million. 1 in 1 million, there was a serious accident in the landing. It had to be at least 1 in 10 million. And that's where we developed mathematical processes to establish, when you took all the components, the autopilot, the ILS, the visual aids, the pilot performance, you were able to put into numbers what the safety levels were. And so today, when you have safety audits thrown at you, and people talk about, doing safety audits and so on, where did that thinking come from? It came from our building on the RE at Bedford. That's where the idea of being able to put numbers onto the safety of what you're providing is. That's where that came from. And the only other people doing it at the time were people in the atomic energy business, and you can understand why. So that whole idea was part of this developing all-weather operations and landing aids came from. Also recognised that it was important, there had to be intensity control. We've discussed that a bit today. The specifications are actually, of the lighting, are to support visibilities in category 3 landing conditions and very low visibility takeoffs. Most of the time you don't use them, don't need them, but they need to be there. That's one of the dilemmas. You're maintaining something which may not be used that often, and the rest of the time it needs to be at a lower intensity. Otherwise you get into glare. If you try to land on 100% at night, you wouldn't want to do it more than once. It really is, it has to be low intensity, and it really do need to be very low intensities are quite adequate. I learned that early on. So there had to be, in this lighting system that was being developed, there had to be adequate brilliancy control, but also in discrete steps. Because if you don't do that, if you give somebody the opportunity to fiddle and turn the knob, you'll get, this pilot wants it a bit higher, that one wants it a bit lower, and it becomes a nightmare. You have to have discrete steps. You can have one of these 5 or 6 steps. Which one would you like? That's the end of it. That's rather important to get regulation, to have it in discrete steps. The third point there is very, very important. And I mentioned the accident in 1968 where the pilot lost reference. When we did a redesign of the lighting, when category 2 and 3 was really right on our doorstep in the visual aids panel, we redesigned the approach lighting. We increased, the biggest thing, we increased the vertical beam spread of the lights. That was inadequate. The higher angles, because in low visibility, where you see the first light, I sat in on hundreds of landings in Cat 3 visibilities. Where you look, if you're in that condition, where you look is not ahead. You look at the cockpit comb. The first light is going to appear on the cockpit combing. That's where it's going to appear. Now, if you think about it, the downward view of the nose is somewhere between 15 and 20 degrees. That's where the first light is going to appear. So you can see you need light at fairly high angles. If it's just as it was originally, the original designs, much shallower, ideal for category 1 and non-precision approaches. But we had to increase to get over that problem of the black hole. Partly so that's very important. That the pilot must be assured that once he's made a decision provided he's below the fog top, and that, if you're making decisions above fog tops, that's a different world, and I can go into that in some detail. But generally, if you've got fog to a height of 500,000 feet, if you're in the fog, then once you see the lighting, with the lighting as it is now, and well, now we understand fog and how its structure is and how it varies. If the lighting is as specified now in Annex 14 and maintained, then once a pilot makes a decision that he has adequate visual references to take control and land the aeroplane, or allow an automatic landing to continue, then he will not, or she will not be embarrassed by suddenly finding there's less visual cues just at the moment when they're about to land. That's an important design parameter, and it depends on having these right beam spreads, right setting angles, properly maintained. But it's crucial to safety. And the final thing, particularly as they're moving into Category 2 from Category 1, realise that you're needing more cues actually in the runway surface, because judging particularly the final bit of the approach to the flare and landing, it's textural cues that the pilot needs. Far more textural cues. Think of grass that the landings in Paris in 1924. It's the grass you can see small movement. When you're moving it, you're looking for these little movements here. You're looking for small displacements before the displacement turns into a velocity, which turns into an acceleration, which you're then trying to stop. You need to be able to see these small movements. You need textual information, I call it, and that's where the touchdown zone lighting came into its own, to fill in this black hole that I mentioned earlier on. That's very important. That's why they're there. It's for that situation where the pilot is manoeuvring close to the ground. And just an illustration of the sort of things you have to think about. Try to illustrate. Take the left-hand side of my diagram, top left-hand one. You're flying in fog, and suddenly you see a row of lights. Okay? Now what's that tell you? It can tell you a number of things. It could actually tell you that you're displaced to the right of it. This is the runway centreline, the approach centreline. It could also mean your aircraft is rolled. It will look exactly the same. You get the same picture. The aircraft is actually rolled, not flying level. It'll look exactly the same as a displacement. The way you sort it out, and this is going back to Calvin, the straight lines and crossbars, put a crossbar in your approach lighting pattern. You can see straight away, you now know that bottom one, you're to the right of it, because that crossbar tells you that. That crossbar wouldn't be horizontal if you were rolled, it would be at an angle. So, simple things like this, which you can now see, we had to discover and find out, and Calvert did a lot of work to show this sort of thing. And the right-hand pair, you can see, if you like, where we were when we didn't have much lighting on the runway. The black hole that can so easily exist, you need to put the lighting on the runway. And that, of course, gives you your biggest problem, is maintaining that lighting, keeping it clean and properly serviceable. It's so vital that you have those textural cues, particularly if the runway is 150 feet, 200 feet wide. The edge lights, you don't see many of them when it's low visibility, and they're all out here, and you want the information here. Sometimes don't recognise actually human vision. You really realise this. You actually can only look at something over about 2 degrees. You can only see the texture, the information, detail. You can only read something that's in 2 degree cone. If you question what I'm saying, try looking, open your book, look at the spine, and without moving your eyes or your head, try and read the text. You can't do it. You have to move your eyes or your head and scan it. It's a very small thing, and so you need the information right there in this very small area ahead of the pilot for him to make these fine judgments, particularly for the flare and landing. The edge lighting won't do it on its own when you can only see a small segment of it. Well, there we were. We were progressing well down. Those people who had the overview of all-weather operations were quite happy. They were gradually nudging down into Category 2, Category 3. As I say, that's why we improved the vertical beam spread. And we got a system that, in the end, did get to 0-0, well, Category 3C, if you like, limited case, certainly British Airways, 25 years ago or so, we got to the point where you could do a landing in 75 metres visibility. Pilot hands off. In fact, if you look at this when you're flying, actually you've landed before you see anything in a 747. It isn't until the nose wheel comes down, hits the ground, you can see anything, and you're in the ground roll by then. That's where we actually got to, and that was the intention, where to get to. So their limits were 75 metres, and 125 for takeoff. And there's just a little point there. We discovered, possibly because of the tragic accident at Tenerife where two 747s ran into each other. Now, part of the reason for that was inadequate visual cues. It was lit and marked and signed as a Category 1 airport, as they then called it. And in Visual Aids Panel, I think I proposed, we stopped calling about lighting Category 1 and Category 2 and 3 approach lighting. It's lighting that can be used in those categories in certain visibilities. You understand that? Because what they did, they got a runway which was only Cat 1 because that was what their ILS was limited to. And yet they were doing takeoffs in what you call Category RVRs, doing certified quite reasonably, taking off at 300 metres. So the marking and lighting and the signage was basically only supporting Category 1 type operations, and yet they were doing operations which were in visibilities were more pertaining to Category 2 and 3. And that was partly, not the whole reason, but it was one of the reasons we attributed to that fatal accident, those two 747s running into each other on the runway. And it so happened then, having, if you like, what she got there, I was asked to do actually for our military, we worked both, our research labs service both the military requirements and the civil. I was asked by the military, without going into too much detail, we've battle type situation, I managed to get a strip which is 5,000 feet long and 100 feet wide. What can I operate on it? How do I operate? And what visualizer? All the electrics are gone. Portable put lights. It'll just be night. It won't be low visibility. But what can I do? And we looked and said, well, yes, you can make portable lights, but 50 candelas omnidirectional, battery operated, and deploy them every 1,000 feet, pairs up to 5,000. Only 12 lights. Okay? And we would put a PAPI on the left-hand side, or an abbreviated PAPI anyway, on the left-hand side. Is that feasible? We flew that with most of the aircraft, the types of aircraft, the size of aircraft. Not per aircraft of jumbo size, but practically everything else in the NATO fleet would be able to operate. We showed this, we did flying trials, we showed it. And in fact, one of the things that pilots said was actually landing on a narrow runway was easier than landing on a wide runway, which might sound contradictory, but actually it confirms what we'd learnt about the need for visual cues here, not out there. In fact, it's easier. What the TDZs do is effectively produce a narrow runway to land on. That's another way of seeing how they function. They provide this narrow runway that gives you good cues, positional cues, for the latter stages of the flare and landing. And we operated that at night. And with that in mind, I went to the CAA and said, I think possibly now, we've done belt and braces, we've got down to this, but do we need all this lighting? It's very expensive, difficult, a lot of maintenance going. Could we reduce the lighting in some way? And they said, well, have a think about it, see what you can do. And what I decided was that after 50 years of lighting development, perhaps we ought to have a review and say how much of this is really needed. And so I did this trial, and there's a report on which I'm basing what I'm going to say now particularly. It's 50 pages long, so you'll understand I can't run you through all the diagrams and so on. You'll have to take on trust these rather bald statements I make. But if you want a copy of the report, you can have it and read. I hope you might find it interesting. I hadn't read it for about 25 years till I'm amazed at some of the things we did actually. But there we are. We did an extensive trials program funded by the Civil Aviation Authority. It was a mixture of simulation trials, because by this time in the 1990s, visuals on the simulators were so good, we reckon they were nearly as good as the real life. But of course we still have the capability of doing fog flying, for real, so we could validate one against the other. And so I set off on that program. And so the question was, well, in what ways can we reduce the amount of lighting beneficially, whilst maintaining or enhancing the levels of safety we've now got? And I came to the conclusion early on that the way we could do something significant was to not mess around with the patterns. The patterns are important, they're well established, but do we need the same number of lights, bearing in mind my thing of a light every 1,000 feet? Do we really need all these lights? Can we reduce the number of lights that make up the pattern? And that's the way I approached it. Because if we can, that'll reduce costs. But if we can do that, maintain the same level of queuing, then that will be beneficial. And actually, at the end of this, we achieved it. What it says, by doing that, the cost of procurement is reduced. And of course, that has implications then on maintenance and number of aircraft, lights you have to maintain. But also, to do it, and I'll mention this more in detail a bit later, to do it, you have to say, this was part of the assumption, that the lighting will achieve those values shown in Annex 14. And so, in the UK, the CAA will look upon possibly implementing some of these changes, which are, some of them, integrated now into Annex 14, provided that you can demonstrate to them that your lighting is up to spec. And if you do that, then you'll save money, but you'll actually enhance safety, because now, for the first time, if you like, you've got a very good reason for making the lighting fully compliant, which it should be anyway. So it's a win-win situation by actually taking a number of lights away, but probably maintaining them. And so there we are. And just a quick reminder of what the various bits of the lighting do. And you can read them for yourself. We're not really talking about the PAPI today, but that's an essential piece of glide slope information. Most of what the maintenance, of course, is, there's a typical nice picture of a runway with Category 3 lighting in it, and a PAPI. That's the sort of starting position, if you like. The approach lighting is all about azimuth alignment. That's what it's all about. And the runway, keeping straight down the runway. That's what it's all about. It's all fairly simple. And I've explained really already what they are, but there we are. It's just a quick summary of what they're doing. This is the report, and that's the title of it. As a result of that work, which was presented to the ICAO Visual Aids panel in late 1990, Annex 14 was removed. And if you look carefully, you'll find various places where, in fact, if you looked at an Annex 14 from the 1980s, you'll find the patterns, the options you can have, particularly as you'll come to in the number of lights in the TDZs and supplementary approach lighting reduce, and that's permitted with certain caveats, like the lighting must be up to standard, but it is possible. Now I hope you can see those. That's a rendition of what was in my diagram report report. Left hand is what you're probably familiar with, what a standard Cat 3 approach lighting system looks like. What we propose in the middle one is reduced lights, particularly in the supplementary approach lights. After all, remember, there are 80 lights in those red berets in the supplementary approach. They were only put in at the behest of comments when we were pushing down into category 2. The pilots were still manually flying the aircraft at 100 feet. I remember flying in the 70s. The autopilot, the best autopilot we had in the airplane, could well deliver you lined up with the edge of the runway. Unheard of today, but that was a situation. You could deliver that far. So the pilot was faced, perhaps with a 100-foot decision, to make a significant manoeuvre, low down. And also, the first thing you need to know, the first thing is, am I on the centreline? So those red berets told him or her, you're on or near the centre, you're within parameters to make a safe landing, or you're not. So a lot of lights to satisfy that question. So there's an obvious target. Can we reduce this number of lights and still maintain the picture, as it were? And the right-hand one was when you go to category 2 and 3, when you certainly need a centreline lighting in. And we looked at where that was really needed. And so that in summary, those previously was what I was proposing, what I'm talking about now. I'll put them down up front so you can see. I did some paper studying first of all, and as my first point, that supplementaries probably today are not, if you pushed it to the extreme, those supplementary approach lights are probably not needed with modern ILSs and with modern autopilot drills a line in the space which is, is so consistent, it's unbelievable almost. It's very, 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 very small compared to the variations we had back in the 70s. So, by all means, it seems sensible to retain something of that picture, but can we do it with a lot less lights? 30-metre spacing on the centre line. ICAO was calling for 15-metre spacing on the centre line. I just felt it wasn't necessary because of my experience. And the fact that at Bedford, where a lot of the flying, I'm emphasising, a lot of the flying was done by the blind lad, years and years of fog flying, developing the RVR decision ratios that is still in use today. That was all done at Bedford on a runway that only had 30-metre space centre lines. Never 15 metres. And why we went to 15 metres, I believe, it was this feeling, well, the lighting isn't very good. We better double up on the number of lights because there'll be lots of outages. And so, because the regulators felt that was belt and braces to be safer, we had twice the number of lights. And even the French wanted to have them at 7.5 metres. That never got into unexported. They wanted 7.5 metres. But by then, they realised their developing glide. So they proposed 7.5 metres, but with lower intensities. Now, if you consider that, the furthest light you can see is determined by the intensity. So they actually reduced safety by increasing the number of lights. It may sound strange, but that's what, if we'd adopted the French proposal, we'd actually made the centre lines less safe. But my contention was, for most cases, 30-metre spacing is perfectly all right. And you say, well, what about the failure case where you're interleaving? I addressed that in the trials, I'll come to it. And do we really need the full length of TDZ? Bearing in mind the aircraft now is delivered, if it's certainly on a coupled approach, well within the 600 metres. And the landing, the aiming point is in the middle. Why this long? Because aircraft floated in the days, they were inaccuracies in height delivery. And here was my proposal in bold figures. The one on the left-hand side, that's a summary of the lights, if you like, in the 1970s were required, the number of lights there, nearly 800, the total, the bottom left-hand side, if you were in category 3. A lot of lights to provide this capability. And what I proposed, reducing the number of lights in the patterns whilst retaining the patterns just as they are, it went down to 503. And I did a quick estimate of what this meant financially, bearing in mind this is late 1990. So you can see if you took an ICAO category 1 runway, as I call it, landings for category 1, and wanted to upgrade so you're operating in category 2 and 3, it would cost you $1 million to buy the equipment and install it. If you wanted to go from category 1 to the proposed category 2, my proposal, that figure would drop from $1 million to £210,000. And similarly, if you wanted to go to category 3, then the figure would go from $1 million down to £600,000. Big savings. You can take the percentage, the numbers will be different. I did look at the cost of living index between there, and probably those numbers, where it says $1 million, you probably need $3 million today to be realistic. But I took this straight out of my report. But you can see the percentage changes, the big savings there are by adopting these things. So how do we do it? A mixture of simulation and flight trials. Simulation came to our aid because it wasn't available when the lighting was being developed in the post-war era up to the 70s. But the modern visuals on simulation are so good and so realistic and so true to type. You really can say, well, what I see in the simulator, if the simulator is set up properly, is very, very similar to real life. So you can use the simulator to do a lot of the work. And it is important, you can say, I might have a show. How many of you have actually been on a flight deck to do an approach and landing on this system? You're all maintaining it. How many of you have actually seen it from up front? That's shattering. That really is. Your management ought to ensure that all your maintenance staff get at least a familiarisation flight periodically, a few approaches to see. Certainly at Bedford, we took our maintenance staff periodically on a half-hour flight, circuits and bumps, going around and around, so to see what they're actually using. I actually find that actually quite shocking. You've never seen this. But at least you could, if they can't arrange a flight, they ought to arrange in a modern simulator. And ask for it. You ought to be able to have that to see what it is you're trying to achieve. So I keep mentioning fog. I could do a whole talk on this, perhaps a webinar we'll do on fog and its vagaries. It's a fascinating, very important. This is a quick summary. We had to put into the simulators realistic fog models. What does the fog actually do? Not what the simulator manufacturers had done, but actually, and this is based on real data over many years. And my colleague produced a fog model in which he could say, you can say, I can say, if you tell me what the RVR is, I can tell you what the pilot will see where on the approach. And if I can measure up to a height of 100 feet, what the fog density is there, I can find out which, this is the case where 10% of the fogs would be worse than this. You'd see less. All these curves would slip down to the right and diminish. So 90% of the cases, you're going to see this or better. That's the one we implemented in the simulation we did, basically on the assumption that from the visual aids alone, they shouldn't generate more than 10% overshoots. There should be 90% landings. It's quite a stiff requirement, but that was the model. And so just to illustrate, if you look down at the bottom, the lines don't go right down to the ground. The reason for that is, of course, the RVR is not measured at ground level. It's when the transmit's on 2 meters high. So they truncate there. So the most right-hand one, you see it truncates at 800 metres. And so if your RVR is 800 metres, in this fog model, the first light you'll see on the top side there is on that where it's at a height of what, 20, 40, 60 odd metres. That's the first light you'll see. And we can tell you which of the lights it was in the approach light of the 3000. And it comes down, and gradually what you see, the fog, mature fog, always gets denser with height. What you can see, this is one of the shortcomings of RVR. It tells you nothing really about, because of the variability from day to day, it tells you nothing about how far you can see at 200 feet. But 10% of the case, it won't be worse than this. You'll see one of the approach lights, and that line there is defined by, as it goes from approach lighting to and the different setting angles. But it's sort of a straight line coming down slightly towards it. It gets to a point where there's a bit of a knee in the curve. That's the end of the approach lighting, and it falls back. So in fact, the distance you can see slightly reduces. This is the mismatch between the approach lighting and the runway. You try and keep, ideally that would be 0. We try and keep it to a min. It isn't very much, but there is a slight, and then it opens up. And what you see when you're rolling along the ground is what the RVR is. So we could choose one of those curves and select that in the fog model we were using in the simulator. So we knew we got authentic fog. It wasn't just an artist's impression. This was genuine data, hard won by a lot of working at 2 o'clock in the morning on the airfield, getting this data. And so our first simulation we did was a 737 sim. And we actually asked the pilots, before they're all qualified for low visibility operations, what's your opinion of the lighting you're given now? Is it insufficient? Is it sufficient? Is it more than sufficient? You'll see the top line there, 55% of them said it's more than sufficient, which is going along with my argument really. It's more. Another 45% said nobody said it wasn't sufficient, which is a good thing really. And then if we then gave them the simulation and of what they currently had, and their opinion was slightly changed. Having done the simulation and thought about it, a few more of them thought it was over provision, and it was sufficient. That it was more than sufficient, going from 55 to 67%. But then, when they saw my proposal and actually flew it, their solution was, what you're offering us is 97% said it's sufficient, and only 7% said it's still more than sufficient. They were the brave ones. They said, you're still giving us too much, we don't need it all. But nobody, the important thing is, nobody said it was insufficient. That was an important result from that first simulation, when we had about 30 pilots from various airlines and some of our test pilots involved. It's quite an extensive trial, a lot of data, which is all in the report. So then the obvious thing was to go fog flying, which we were set up to do. We've been doing it for 25 years. So a whole winter of fog flying. And I got one of my staff to run this. But it's very difficult to fog fly, because if you're going to go flying in fog, it's usually in our situation, out of operating hours, because, you know, as a research establishment, we don't do 24/7. So you're going to have to call people in either early in the morning or stay on late at night. And it was a rough figure. To keep the airport open, the aircraft serviced, maintained, flown by test pilots, having flight safety people there, the ambulance and everybody need to be there for it to be legal. It was about 100 people you had to call in and coordinate. So an early morning start, if we got fog, somebody who was running the trial would call, we'd go fog flying, 7 o'clock in the morning, rapid phone calls, and get airborne before 8 o'clock on the lift. Quite difficult to do, and particularly if you're not having a lot of fog that winter. So we managed a significant amount of fog flying, all done by our test team flying, I have to say, who had done a lot of fog flying for real in their previous seasons. They were very experienced. They knew what they were looking for. And so we limited ourselves to when the visibilities were into the category 3 type visibilities. And we did do little things. We took one of the lights out in the centreline to see if the pilots noticed there was a light. Didn't even notice. Nobody commented, even though there was a light. But the pilots, our pilots, had also taken part in the 737 simulation. They were part of the cohort there. And to sort of press the thing and see how flexible it was. We had 3 different approaches, techniques. The first one was fairly old hat. And I guess today very few people, certainly in the major airlines, would ever do this. But it presses the boundaries of how robust is the system. Not even a coupled approach. It would be a flight directed approach. The pilot would have to fly his flight director head down in the cockpit to establish the glide path and line up until he got to decision height called look up and then do a manual landing. That was the sort of thing that was going on in the 70s, trying to make category 2 really work. That really isn't perhaps very feasible today. Not many pilots would have seen doing that probably on the major airlines certainly. But you know that stresses the solution, you know, because if it works in that, then it'll probably work in the more benign situation. Then doing an automatic approach, moving on from that, so the pilot isn't handling the aeroplane until he gets to decision height. Then this is typical category 2, coupled down to 100 feet, say visuals, pilot makes a decision, land, takes control of the aeroplane, lands the aeroplane, what he sees. And then the final one is the 0-0 situation, automatic landing, where the pilot doesn't touch the controls until the aircraft is rolling along the runway. So all those are included in the simulation, in the flight. So whilst we had a limited number of approaches, we still were able to try quite a lot of techniques and approaches which really pushed the boundaries of whether this lighting was adequate. And so our results were that, first of all, what we got from the simulation, from the fog, was very similar to the results we got from the 737 simulation. That was important for 2 things. One, it gave us more data and real life, you know, actual fog flying data, which is good street cred, as it were. But also, because we were doing the same experiment in flying as we were in the simulator, then the simulator was shown we could use the simulator extensively to increase our database, to show it to more people. And the results we got would be credible in the real world. So that was an important solution. And we also came to the conclusion that a 30-metre runway spacing is sufficient in all visibilities. And I'm not just talking about landings here, I'm talking about takeoffs. Is all sufficient. But the third point, the pilots kept stressing, the threshold must be good. We must have that green threshold. And I know from flying, they're sitting there between the pilots looking. When you see that green bar go underneath you, there's a sense of relief. At least you're over the runway. And when you put you're not going to land in the soft. It's really very important in the process to know. It's a good signpost. Yes, we're at the runway now. And very shortly we'll be making the landing. That's very important. So in your maintenance, make sure your runway threshold, and the stop end as well, I guess, is up to specification. We had some discussion about the length of TDZs, whether we needed to have 900 metres, 300. It was, well, yes, you know, possibly 600 metres, but no clear definition. And you can see the point. We actually flew with reduced barrettes, only 2 lights in each barrette instead of 4. We modified our lighting patterns at Bedford to do that. But there was some discussion about, well, if it's a 4.5 metre light bar with lights on it, do you put the inner two out, or do these two adjacent. So you've got a bar that's 1.5 metres wide. They're not quite sure, more consideration needed. And there were some concerns about failure modes, which we weren't able to do in our flying trip. What happens, classically, if the interleaving fails on the runway centre line? It's a good way of putting it. What happens if we lose a circuit suddenly when the aircraft is landing or taking off? The other question was, well, he did it in a 737. What about the big airplanes? And so we did a second simulation, similar in many ways to the first one, where we're looking at those issues particularly that we might find because they were big airplanes. We got airline cooperation, British Airways particularly. They actually rostered line pilots. Instead of going flying for them, they came to our simulator for 4 hours, and that was their flying duties for the day. They were very confident, mainly from British Airways. There were others. It was a 747 simulator from BA at Cranebank we actually used. So we got genuine pilots who were used to operating and were certified to operate in very low visibilities. And they were operating 747-400s. Many of them, when we questioned them, they had operated in low visibilities. I've had lots of discussions, particularly in the States, where you get a lot of American pilots. Oh, we operate to Cat 1 minimums. So they're the experts in landing in 600 metres and 200-foot decision heights. They're probably spending their whole life in the southern states. Whilst they're cleared operation to do it, they've never done it. And yet, because I'm a pilot and I'm certified to do it, I'm the expert, so you have to listen to them. They've got no experience at all. You know, I wanted pilots that had actually been used to this, either for real and or the British Airways trained in their simulators. So these were pilots who knew what we were talking about. And so they've got a lot of experience in doing this. And that's a typical what we asked them to do in their duty. So 12 runs. On the left-hand side, you can see what the conditions were. You can see the visibilities we did it in, and then what they were asked to do, the third column, takeoffs, landings, and then with various variations in the lighting. And as we go down, you can see there's decision heights come in. The first one's a takeoff, the decision heights that they were using, and then there's an auto land in there, and then there's we put a crosswind in to make things a little more difficult for the pilots. You know, if you're landing in a crosswind, does that affect the results? And then this is the crucial bit in many ways for the pilots. What happens if the centreline lighting reverts to 60 metre spacing because one of my circuits fails? We tested that very rigorously. We did things where we failed the centreline lighting to 60 metre spacing before V1. Of course, V1 is the critical point. That's the decision point in takeoff. If you haven't reached V1, then you abort, you bring the aircraft to a stop, keeping it straight on the runway. Typical thing that may happen, we tested it to see if there are any problems with that sort of scenario, if the lighting failed. Then we went to lights failing approximately 120 knots. The aircraft's gone beyond V1. It's committed to takeoff. Are they able to keep the aircraft straight and do a takeoff on this limited lighting of 60 metre spacing? And then and so on down, and you can see the test case we did, trying to address this issue of if we get failures in your reduced pattern, is it still robust, or does it all fall apart? That was a nice set. That's a typical matrix. We run one pilot through it. And our simulator results were very, very similar to what we got in the earlier simulation and in fog flying, but with the additional knowledge that we looked at failure cases and things like that. So you can see, and basically what came out of that was, no, even for the large wide bodies, there's no reason not to go for these reduced lighting provisions. They will adequately and safely provide for operations, which is a very important conclusion, of course. And we took all of this stuff then to ICAO, the visual aids panel, and a big discussion, basically based on my report, most of it, because some of it was after that. But what I've been explaining up to now, they took this in and we had a big discussion about it after about 18 months of this thing. And the result of that was, ICAO said, well, will you do one more simulation? There are a few odds and ends we want to tidy up. So we did an additional simulation. They wanted, well, could we have an even bigger database, some more pilots? We could do that. And you can see the other things we did there. And then finally, the bottom one, the Canadians had put on the table some idea of reduced approach light, very radically different to this. We put it as a favour, if you like. We did it for free for the visual aids panel, and the pilots said it was totally inadequate. That was, if you like, the end of the. So we did 3 simulator trials and a fog flying trials. So we got a lot of data. But that second point, it has to be lighting that is up to spec. And I know that the UK CAA only countenance using the reduced lighting if you're able to demonstrate that your lighting is up to spec. That's important. Well, I think, in a way, I'll stop there, time-wise.
Right. Well, thank you very much, Tony, for that excellent presentation. Very much appreciated. So in today's webinar, you've told us very concisely about the development of the visual aids, how they were developed, why they were developed, how pilots actually use them, and how decades of research, which you've been at the forefront, have led to smarter maintenance practices and opportunities to reduce unnecessary infrastructure without compromising safety. You also pointed out at the end of the webinar how we must maintain that infrastructure. That is absolutely key to safety and efficiency. So going through the period, I took away from the at a very early stage, we talk about you can't manage what you don't measure, and there were numbers put on even on safety, and so you talked about reducing from 1 accident per million to 1 per 10 million. But as someone that's flown an awful lot of times, I can tell you that I'm not sure I like 1 per 10 million, but I wonder if that's still a relevant number. But certainly it's a lot safer than it ever used to be. But we should always remember that from an aviation standpoint, the costs associated with go-arounds, diversions are huge to the industry, and the inconvenience. And if you've ever landed in a different county, state, country, even to that which you intended to, and your car is parked in another place, you've got other appointments, you've got ongoing flights, that is a pretty shocking experience. Causes huge disruption, massive cost to the industry. But obviously safety is paramount. That's why it's done. But it would be best if we could avoid that sort of situation. And we also heard about the light design should be such that when you reach the decision height, your visibility of the lighting, which is what you're seeing in low vis, should increase, not decrease. And and Tony always refers to the black hole. So when we come over the 20,000 candela approach lighting, we then hit the runway lighting and particularly with inset fixtures that are impacted with the airfield dirt, contamination, the rain, snow, ice, whatever it is, sand, that all compromises that lighting much more than any approach lighting. So you can, if it's not properly maintained, you achieve what is effectively a black hole, which is highly unsafe. And then of course we have very interesting tales of how you developed the standards and wrote your report. Tony's offered to send this report to anyone. If you put in your comments at the end of this webinar, if you send us an email, we will gladly share with you a copy of Tony's report. And I think you'll find that very interesting. You'll learn a great deal from it. So I highly recommend it. And thus we reached the end of the webinar. Now, one question has come in, Tony. Are you there, Tony? Can you hear me?
Yeah, I'm here. Yeah.
Good. Yes, and this concerns PAPIs actually, which obviously in relation to obviously you at the you've developed. So one of our participants have said that noted that previously the ADM said that the sharp transition characteristic should be verified as an operational distance of at least 2 kilometers, but noted that this was in edition 4, but this has been omitted from the latest edition and replaced with only partially with a check at 300 meters instead. Do you know how this has come about? What is your opinion on this? When you talk about the importance of conspicuity.
Well, it's interesting because, of course, in my presentation, I'd only got only an hour. I couldn't cover all the visual aids like signs and so on. I limited myself to the approach and runway lighting. But of course, PAPI is an integral part of the approach equipment, very important. And since that presentation, it's been brought to my attention what you're just saying, the difference between the two versions. And I find that quite alarming because something that I could have said, and perhaps I should, about fundamentals, is when you're looking about visual aids, there are criteria that you have to meet if a visual aid is going to be effective. First of all, it has to be conspicuous, then it has to be legible, then it has to be comprehensible, and then it has to be credible. In other words, is it very obvious where it is? When I see it, can I read the message it's got for me? When I've seen that message, is it comprehensible? Can I understand it? And finally, do I have experience of this lighting or this visual aid to say, well, I believe what it's telling me? And the first one of those is conspicuity. Now, this is important for all the lighting. We talked about just seeing the approach lighting just over the nose of the aircraft. You know where to look in low visibility. You don't look ahead, you look over the cockpit because that's where your first light is going to appear. You know where to look. When you're doing an approach, not necessarily, won't be in low visibility, not very low anyway, could be category 1, but times when you're perhaps using the PAPI as your major aid, the conspicuity is an important issue. Bearing in mind, if you will, that when a pilot is doing the final approach, he's looking at a lot of things, not just staring at the PAPI. He's going to look at the whole runway, his lineup. A lot of things are going on. And so if there's something that he needs to see related to the PAPI, it has to be conspicuous. If it isn't conspicuous, the rest of it is worthless. And to make it conspicuous, the original PAPI design had a 5-to-1 intensity difference between the red and the white signals. Now that was inherent in the way we made the design. My original design, I was looking for a red-white system using the same concepts as Varsi, reds and whites telling you where you were. And so that was in my mind. I wanted a red-white system that was easily understood and was more precise than Varsi. when we started doing the experimental work with it, the test pilot said, yes, this is a big improvement. The one thing they highlighted was that when they were in this busy phase, the fact that they said the thing clicks at you, they said that the PAPI system clicks, and that draws our attention, that we need to pay attention. That's the conspicuity. That click is the conspicuity. The number of red and white lights, which you then see, that's the legibility. That's the message you then take from the PAPI, the number of red and white lights and how they're changing. That's the legibility of it. And of course, it's comprehensible and so on. But if you take away that 5-to-1 change between intensities, between the red and the white, which is effectively like making a flashing light. If you take a light at 100% and you switch it swiftly to 15%, the casual observers say there's a flashing light. That's what it is. The pilot stressed that very early on. It's the click that is so important from a flight safety point of view. It knows I have to do something. And below 200 feet, we had examples when we did the development and had equipment at Heathrow. Pilots commented on a number of occasions, I was below 200 feet, I was nice and stable, and suddenly I got into a wind shear, which is a sudden change of direction of wind direction, load out, and I was decelerating very rapidly into the approach lighting. And the first thing that told me was not the instrumentation in the aircraft, it was this click of the PAPI that told me I was in a wind shear situation. And so it's a crucial part of the safety that the PAPI gives you below 200 feet, particularly, and but administratively, without, as far as I can see, any experimental work and real understanding of how the PAPI works. I have to say, I feel whoever made this decision didn't really know what they were doing. I'll be as blunt as that.
Well, that's thank you for that, Tony. Now we need to, and certainly something we will address with the visual aids working group. Now, the next question, you've attracted, obviously your reputation goes before you. Another question on PAPI. This is from Anthony Lawrence at MOD. On MOD basis, we've funded a project to replace our PAPIs, and they have a couple of questions. He has a couple of questions. Can existing PAPI foundations and duct routes be reused, or do you have to have new? Do you have to have new plinths? Do you have to have new frangible mounts or new cabling routes, or can you use the existing ones?
I think that's going to depend on what you're purchasing. If you're buying new equipment, will it sit on the existing?
I think this is knowing this at the MOD. I think this is aimed at a particular manufacturer that has modified their halogen PAPI, and they now have an LED range that's based on the using the same platforms.
Yeah, but if it's using the same platforms, and you can, if it's a genuine PAPI with the sharp transition I've been talking about, if it fits on the base and it's the right power supplies, the right brilliancy control, why not? I would, if I was purchasing, I would want to have confirmation that in fact this new equipment does in fact meet the full PAPI specification in terms of things that you can measure, which is intensity, beam spread, color, and sharpness of transition.
Right.
By the
So
way, you can't manage by a flight check. None of those can you manage in a flight check.
No, this is quite interesting because I don't know this particular installation, but I know of I imagine I know the PAPI that's been used here, because there's only one I know only one I'm aware of that has this characteristic. And on one installation, because it's an LED, you need to look very closely at the power supply, and I believe in the particular case I was at, there was some discussion, but first of all, the CCR hadn't been tapped down, and so this resulted in the PAPI giving far less intensity than it was designed to give. So be very careful about that. You need to look at the power supply requirements, and I believe subsequently the PAPI was the CCRs were, well, the PAPI installation was reversed on that night, and subsequently it was reinstalled with new CCRs. And the second thing was a similar event occurred in another country using the same PAPI, where there was no photometric testing, and it wasn't discovered until the pilot asked air traffic control what had happened to the PAPI, because they couldn't see it, because on the ground it was not obvious to clear and obvious to the people on the airport that the PAPI was emitting something like well, I believe it was certainly less than 10,000. I believe it may have been 5,000 candela. So on a 10-mile approach, it was just not visible at all. This was on the white side, so much less on the red. So certainly you need to be very, very careful of this sort of thing. And the follow-up question, go on, Tony.
I think my response would be to the person who is selling you this equipment is the output that if we install it as you tell us to, is the output going to be compliant with the Annex 14 specification? And please demonstrate that it is before we procure it.
In this, yeah, I mean, in this case, in the first case, at least it was, I mean, it was clear in the instructions what needed to be done, but somebody had to read the instructions and follow them. And the second,
Robert,
yep.
Looking at the questions, he talks about the old PAPI seemed to bounce around. That would make me question the foundations for the original units. And the FAA also has a requirement for the power control to be outside the runway safety area, and if possible, outside the runway object free area. So depending on where the original installation was and where the new one is going in, that might have an impact as well.
Absolutely. Yeah.
Yeah.
So, of course, in the United States, you have the unusual situation where the PAPI is not the responsibility of the airport. It's the responsibility of the FAA. Is that universal?
Varies by site.
It's not. So there are some where the airports actually do it as well, are there?
There's some where the FAA maintains them. There's some where the airport maintains them. Yes.
Okay. Okay.
I think my understanding of that, Robert, is that when it comes to funding, if you apply for federal funding, you can get it for PAPI if it's an approach aid, but not if it's a runway aid.
Right. Yes. I believe that's so. So, and then the question also is, what maintenance burden should operators expect? Cleaning frequency and recalibration frequency of PAPIs. Anyone want to go at that one? I mean, ultimately, the operator, the provider of the PAPI, the manufacturer of the PAPI, will have the maintenance guidance in their instructions. In the United States, there are in ADM Part 4. There are stated maintenance recommended in the stated recommendations of good practice. In the MAs and SFG 20 in the UK for military installations, there are recommendations regarding the maintenance and ongoing testing of PAPI compliance. Similarly, in the USCs, the United States, and I think all national and international regulators have recommendations. But clearly, I think that the first port of call is to look at the specific manual associated with that type of PAPI when it comes to looking at the frequency and the nature of the maintenance steps. But of course, then local conditions will all have a significant bearing on that.
Yes, I think that's true of all your visual aids. It is, in a sense, type specific, depends on your airport pollutants and how when you have the initial installation, you need to be monitoring it fairly frequently and establishing what frequency you actually need to apply for the monitoring to maintain the required level of maintenance. And it may vary quite a lot from location to location. That's work that needs to be done during the initial installation operational time.
Yeah. I just also we had another question again. What is the reason why the PAPI is what is the reason why the PAPI is frequently busted? What is the reason that? So what does she say over the? What are the reasons why they're frequently busted? I think we're talking about halogen. Is it, why do the lamps break on the PAPIs? Well, on the halogen PAPIs. Well, I mean that's in the nature of halogen PAPI. The lamp life is considerably less than LED PAPIs. Although I'm a big fan of halogen PAPIs. I'm not going to get into the LED halogen discussion right now, but I would point out that I think it's very important to have the correct lamp for the PAPI, and I strongly recommend the OEM lamp is used, not a substitute. I've seen a number of instances where incorrect substitutes have been used. I remember one instance where a household projector bulb was, although seemingly conforming to the requirements of the airport to PAPI, was used, and yes, it worked, but only for an incredibly short time. And the disruption to operations when PAPI bulbs go is significant. So stick with the OEM is my recommendation. Any other comments there?
Yes, I would make a comment about tungsten halogen. In a sense, it's almost past technology, but it's still out there in real term. When it was introduced, says how old I am, when we first introduced tungsten halogen lamps, there were a lot of failures. And what that was down to was the fact that tungsten halogen bulbs do not like being underrun. If they're not run at the rated current, then if you run them at very small percentages, the halogen cycle doesn't operate. And what happens is that your filament then evaporates onto the inner surface of the bulb and effectively makes a window, a black window there. And so then the bulb overheats and explodes. That was happening with a lot of taxiway lighting initially at Heathrow, I remember. They found that the life of the tungsten halogens was a lot less than it had been with the ordinary tungsten light, because they were underrunning it a lot of the time. The technology was such that this effectively shortened the life. So I don't know whether that's at all relevant to this particular question.
Right. Well, I mean, without knowing the specifics, I mean, I think clearly if somebody has a problem with their PAPI, their first reference should be to the manufacturer, and then look again. We talk about measurement. You should be measuring using a CMS, a maintenance CMMS. Computerized maintenance management system. You should be measuring the intervals at which you change your lamps, so if this is a one-off aberration, the performance of different makes or manufacture of lamps that you're using, and you should be comparing that to the datum being being the manufacturer's recommended lifespan and their maintenance practices to determine if there is something abnormal happening here. Clearly a halogen's going to be a lot less than an LED, but
Robert?
is it? Yes?
I was going to say the current is critical on the halogen lamps. Just 1/10 of an amp too high shortens the lamp life significantly, and 1/10 of an amp too low doesn't provide the right output. And additionally, if there's vibration in the area, or vibration on those units, it'll cause the filaments to fail early. So the current output on it going to the unit is critical to check and look for any vibration that might be going on in the area.
Yes, absolutely. And we heard about vibration in one of the earlier questions. And obviously the webinar will be posted onto our site with access to the paper that Tony has kindly offered to share with you all. So thank you very much for that. We're going to take a summer break now. We're back on, Damon, if you could tell me.
September the 29th.
On September the 29th now, where we'll be hosting a case study from an airport concerning their maintenance practices, the challenges they face and how they overcome them. And in the meantime, I wish you all a very good summer. I hope all your teams somehow conspire to jointly win the World Cup for soccer, and wish you a very happy next couple of months. And so thank you very much for participating. Thank you to the panel for your contributions, and especially to Tony for putting together this presentation with the able assistance of Damon, that you can also see on your screen, and both of them have done a huge amount of work to make this happen. So thank you guys, and I look forward to seeing you all after your summer holidays. Good afternoon, good evening, good morning.
Thank you.
Thank you,
Bye.
Robert. Same to you.
Thank you. Bye.
Thank you.